So what happens is to solve for it, right, you look at your equation and you say, okay, in the y direction we have equilibrium here. So on the left-hand side we can say that ft minus fg equals 0. It was given in the problem, if you recall, that the object was at rest. It was in equilibrium. It was at rest. It was at rest. It was given. You have to make the assumption it's equilibrium then. So this becomes ft equals fg, whereas on the right side over here we have a scenario where it becomes 2ft, because there's two ropes pulling up, minus fg equals 0. So therefore 2ft's equals fg. So therefore the tension on this side is fg divided by 2. So the tension in the first case is equal to the weight. The tension in each rope in the second case is the weight divided by 2. So which case has more tension? The first case. It's equal to the weight, whereas this is half of the weight. Okay? First case has more tension in it. The common mistake, again, let me just point this out. The common mistake was here. When people saw the person pulling on the rope, they put another force pulling up here and wrote like FP or something. But again, the person affects the rope and only the rope affects the object. So that's why only tension is shown here. Other stuff. Other topics and the things you've struggled with, maybe you've been studying the last couple of nights, like I've been mentioning, problems that you've run into where you didn't get the right answer, or you're not sure of the answer, or the methodology behind it. What are you thinking? Chris, go ahead.
There's another one like this on a test. It was like a kid on a slide, I guess. And one slide was like completely banked, like at a 45-degree angle, and the other one was like more like a...
Got it. So the question for this one, good question. Hey, these are like the common ones that people struggle with, so I'm glad you asked this one too, both of those questions now. So this was one scenario, and this was the second scenario. Yeah? So one was pretty much curved and one was flat. But the concept was that both of these had the same exact height h. So in both cases, the person, it was like a boy or a girl sliding down the actual thing, slid from the same height. It doesn't matter how far you go horizontally, but the same height doesn't matter. So to exaggerate this a little bit more if I want to, I could even take this one over here. Oops. Maybe just draw it even a little bit further to show like how far this person is going to end up over here. Okay? Because the height is what matters. So let's talk about this. It says the person is sliding down both of these ramps from the same initial height, and in both cases, the person is starting from rest. Determine in which scenario this person will have a higher velocity at the bottom of the ramp. The bottom. What was the answer? Who remembers? What was the answer? Because a couple of you got this right for sure. Which person has a higher velocity at the bottom of the ramp? All right, let's talk about it then. So let's say this person here starts. Well, if I think about the person starting at the top, so I'm looking right here now. Okay, if I think about the person starting at the top, what kind of energy does this person have at the top? What kind of energy? It's got potential to start. Okay, and once this person reaches what we're considering ground level, let's draw ourselves a ground level line here. We denote that with PE equals 0 always. Once the person reaches that ground level, what kind of energy does this person have? What kind of energy is the question? Only kinetic energy here. Only kinetic. Okay, yes?
Because in the second one, each bottom it would slow down. It's flatter. It's more flat.
Okay, I could see that, but I like the idea because you're seeing this little region over here and saying like they might stop. Assume no friction though. We had no friction in this problem. So that little flat region, it's not like he's going to slow down because of that flat region. See what I'm saying? So because there's no friction, we can look at this a little. If there were friction, absolutely. Then the more distance you cover, the more friction is acting on you. So it would probably be slower in this case if there were friction. She's absolutely right. It would be slower in this case if there were friction, because friction acts for a longer curve than that direct line. But there's no friction right now. Okay? No friction.
Would the second one be quicker? Like the steeper at the beginning will ask for like a quicker acceleration going down?
Yeah, so that's the other rationale is that like you look at the slope of the first ramp and the slope of the second ramp, you think, oh, he's going to accelerate really quick in the beginning, so you pick up a lot of speed. But then the ramp gets really flat, so those kind of balance each other out. But I like the idea. See what Will was asking? He said, look at the curvature here. Look how steep this drop is. So it's like the person is dropping off, whereas the first one he's going like a gradual slope. But the fact is, at the bottom, it flattens out. So this drop off and this flatten out, they balance each other out. Again, assuming no friction. If there were friction, it would be different. So why did I bring up energy? Nobody's pointed that out yet. We talked about that. Why did I bring up energy? Why did I say potential and kinetic for the first one? James, what do you think?
They both start off with the same potential.
Yeah. In both cases, so let's go to the far right now. This one has potential to start, and again, at the end, this person has kinetic energy at the end. So both scenarios are the same, actually. Even though they look different, you start with potential, you end with kinetic. All the potential you have to start, where does it all go? It all goes to kinetic. So in both cases, you're going to have the exact same velocity at the bottom. If I think about this potential energy at the start equals the kinetic at the bottom, right? Well, in the second case, we've got potential at the top, and that equals kinetic at the bottom. If they both start with the same potential, they both have to end with the same kinetic. Conservation of energy tells us this. You cannot lose or gain energy. Now, if we have friction, we add that Q on here, right? At the end, it would be plus Q and plus Q over here. And this is what Isabel was mentioning with the curvature here. So if I had friction, this plus Q might be like 5 joules of energy loss. But this energy loss would be more than 5 because it's taking a longer path. Friction is acting on it for a longer time period, a longer distance, I should say. It's a curved arc length, not distance. But friction acts on it this entire time here, whereas here friction acts on it. It's less friction. It might be like 5 joules of loss of energy to friction. Here it might be like 10 joules of energy loss to friction. And if that were the case, then the kinetic energies would differ. But because there's no friction involved here, if I started both problems with 10 joules of potential based on the height, well, that means this is 10 and this is 10. Well, then both kinetic energies are just 10, right? At the end of the problem. And it's the same person, so as a result, they must have the same velocity at the end. If you and I have the exact same kinetic energy and the exact same mass, well, kinetic energy is mass and velocity. If our masses are the same, the velocities have to be the same for the kinetic energies to be the same. So that's the process we undergo here. Now, let's pause for a second, because this is the midterm, so it's going to be a little bit like, not more difficult, but I'm putting things together, right? We talk about this, how topics are going to be intertwined. So now we look at this problem and think about energy loss. So this one would have Q loss here. This one would have Q loss. We'll call this Q loss 1. We'll call this Q loss number 2. So if we did consider friction, Q loss 1 would be less than Q loss 2. The reasoning, again, what causes friction? Work. As I apply a force on this, it causes it to move, and then friction, right? I apply force causing it to move. Friction acts on it from the time I let go, actually the whole time, really. From the time I let go, friction is acting to slow it down until it gets to here. So this takes a certain amount of interaction in a distance. There's more interaction occurring, God bless you, between the object and the ramp because this is a longer curve than this straight line. If you don't believe me, think about it. If I walked around the room and ended up where Chris was, take a curved arc around the room, end up where Chris is, or if I walk directly to Chris, obviously the direct line is shorter, right? Taking the curve is always longer. We know that because of displacement and distance. So this will be a longer distance traveled than this will be. So as a result, this Q loss will be less than this one because this is acting for a longer time. If friction acts on this eraser for a certain distance, and then it acts for even more of a distance, it means there's more friction acting. So Q loss 2 might be, let's say, 4 joules, where Q loss 1 would only be 3 joules. And then in that case, here's how the problem would change. So this would be a Q we'd have to subtract over. And then as a result, our answers would change also. The first object would have 7 joules of kinetic energy left, while the second object, or the second person, the same mass, would only have 6 left. Again, because there's more energy loss to friction in the second case, if friction were considered. So we've looked at this problem the same way as we analyzed it on the test and in class, and now with, I think, a better approach by looking at the actual effect of friction on it. So consider both options, right? On the test, it's really important that If a problem doesn't specify friction is there, don't include it. Is that clear what I'm saying? All year, what we've done, and especially with kinematics, with projectile motion, we assumed no friction. We didn't even incorporate friction until we got to Newton's laws. So anything from early on in the year, all that stuff with one-dimensional and two-dimensional motion, there is no friction in those problems. We assume none. When you get to conservation of energy, if I want there to be friction, I will mention that there's a mu value, and then you know there's friction. Or Q loss, or there's air resistance, so there's friction, right? I will make sure to mention that on the test. If you don't hear about friction, you assume no friction. No? Good question, Chris. Very good. What other stuff that you've been looking at on your own that's been troubling you, maybe? We got several topics, right? We got one-dimensional motion, just left to right or up and down by themselves. Then we've got projectile motion. Then we've got vectors, like vector analysis. Then we've got work and energy. Newton's laws first, then work and energy, and then momentum and collisions and impulse. There's a lot of stuff to discuss. What do you want to work on? Which of those is something that you're really confused or not certain of? And think about it. We didn't go over everything in the formula sheet. We covered them all. We didn't do a lot of problems for all of them. What problems did you, as we were looking at the formula sheet yesterday, did you say I don't really know how to do this, so I want to take a look at an example? Vectors? Sure. Let me give you a sample vector problem that could be something similar. By the way, the vector problem that was given on your actual test is a great example. So, and those questions are all on Moodle. You know that, right? All the math problems from all of your tests are on Moodle. Those are another resource, obviously, for more math problems to look at. But I also put a sample vector problem after the review document in those 10 problems. That's another good one to look at. But let me just give you one so you can do it today together. We'll start with a basic one, and then you guys can extrapolate a little bit further. So let's say that a person walks, a person walks 10 miles, a long walk. So a person walks 10 miles, or drives, it doesn't matter, 10 miles at an angle of 30 degrees northeast. Before I draw any more figures or any more notation here. Northeast, show me real quick. Which way is northeast? Good. This way, right? You're all clear on this? This is north. So when I think northeast, what did I teach you guys? North of east, right? So which way is east? So then you go north of east. So that's the angle measurement right there. Is that clear what I'm saying? When you hear northeast, it's the angle above east. North of east. Southeast is the angle below. It's never the angle with the vertical. It's not east-north. You've never heard that before. Nobody's ever said east-north. It's northeast. Because you're measuring the angle north of east. So here's your east line right here. That's what east would look like, right? This is the angle north of east. How much north? Let's say in this case, 35 degrees. So a person walks or drives or whatever, or bikes 10 miles at an angle of 35 degrees north of east. North of east. Then the person moves... God bless you. I was going to cough. Then the person moves horizontally 6 miles east. And finally comes and walks back toward the area at, let's just go south for this one, 3 miles south. Okay, so let me quickly just reiterate what the problem state. Because part of this is about drawing the diagram, right? You notice that from your test? Part of it is really just being able to draw the diagram. So the problem would say the following, if you're the type that likes to type stuff and have it later so you can look at it. A person drives, walks, bikes, whatever, 10 miles, again, a person drives or walks 10 miles northeast at an angle of 35 degrees. The person then stops and walks 6 miles east. Person then stops and walks 6 miles east. Finally, the person stops again and walks 3 miles south. Determine the overall displacement of this person. What do I mean? Overall displacement. What does that mean? What is it referring to? Overall displacement. How do I indicate that on the diagram?
Draw a line from the original starting point to the final.
Very good. So overall displacement always means beginning to ending. So just connect your starting and your final. Connect your starting point and your final point. That's what you're looking for right there. You are looking for the length of that yellow line and the angle it makes above the dashed red line. Or below, depending on where it is, right? Or below, it could be above or below. So we did this in like two different ways. First, I showed you guys the breakdown of how to find the components of triangles. And then I also went into a method that was called table method, where you organized everything with x and y and the cosine sine. I can do both approaches, it doesn't matter here. But I want you to visualize what's happening. So for a minute, just look up. You don't have to draw this, but just look up. So this person, when he or she walks 10 miles like this, could really be thought of as going like the following. Ready? The person could walk horizontally first and then walk vertically, and that would have the same overall effect. They could walk vertically and then walk horizontally, and it would have the same overall effect as walking like this. So what I need to do is look at the 10 miles and break it into the y component and the x component. And this is what we did with the table method. Then this is only x, and then this is only y. This is positive in the x. This part is negative in the y. So we have to consider these different facets because it's going to change the signs that we're going to use. So if I'm looking at the table method, which I think is pretty easy to use, okay, I look at the table method, and I don't know if I did x and y over here. Did I do x and y over here with you guys, or x and y up here? Do you remember or no? I forget. I've done the table method many different ways. On the side, so I put like the horizontal component and vertical component. Okay. So the x component of the vector, the y component of the vector. And in this case, we have 3 vectors overall. So the first vector is the 10 miles at 35 degrees northeast. The second vector is 6 miles east. And finally, the third one is 3 miles south. So those are the 3 vectors we have to break into components. Now, the one that's going east and south only, you don't have to worry much about those components because it doesn't have 2 parts to it. But the first one does. How do I find my x component? The x component of any vector whatsoever. And you can go right to the formula sheet if you forget. Or you could remember from velocity, or you'll find VIX and VIY. How did you find VIX and VIY? What'd you do?
Use like cosine.
Yeah. So for the x component, you multiply it by the cosine of the angle. So this becomes 10 cosine 35. Whatever that is, we'll calculate it in a minute with a calculator. But for now, that's what we have for the x component of that. The y component is similar. What's the one difference?
Sine.
It's sine instead of cosine. Now, I'm going to pause because I know that on the test some of you still had trouble with this when we did this, so I want to make sure it's clear. So let me show you on the figure where these lengths are. So this right here, I'll use green, okay? It's not actually on the diagram, I'm just drawing something. This right here is the vertical component. Can you even see that? Is that better? Yeah. That's the vertical component of that, and that's really just 10 sine 35. That's that second part there. And then this is the horizontal component, which is 10 cos 35. So when you look in the actual, and there's a right triangle there if you take a look at it clearly. When you look at the actual table, the numbers make sense. 10 cos 35, that's how far he traveled in the x, or she traveled in the x. And then in the y, this person traveled 10 sine 35 straight upward. That's this right here. So instead of taking the 10-mile route, we can think of it as doing this and this. So we break this at an angle into components. These two don't have to be broken because they're not at angles. What does east mean to you? Does east mean in the x or in the y direction? Right off the bat. Just answer that to start. Chris? In the x. Is it a positive x or a negative x for east? It's a positive. So Chris is right by stating those two things. It's east is in the x and it's positive. So this is just a positive 6. This is a 0. Because the second leg of the trip involved no vertical motion. It was just a 6-mile leg. The third leg of the trip involved a 3-mile part going south. 3 miles south. What do I put in these spots, Amy? Very good. The person does not move left to right, so this is going to be 0. But the person moves down 3. So put a -3 in the y spot there. So again, we're not breaking things into components if they're not at angles. Other than 90 degrees and stuff. Those are 90 degrees, right? Okay? If they're not at an angle, you don't have to break them into components. Just think visually about how the person's moving. If they're moving this way, negative in the x. This way, positive in the x. Positive in the y, negative in the y. And then we just simply add across. That's all we have to do is add those numbers straight across. So 10 cos 35 plus 6. What do we get? 10 cos 35 plus 6. Just give me a quick number so we can actually finish this. Make sure your calculator is in degree mode. What do we get? Go ahead, Katie. 14.19, okay. And these are called my resultants. We'll talk about that. We used that phrase already. All right, in the y direction, 10 sine 35 plus -3 or -3, either way. Chris? 2.75, all right, that sounds right. And just look for a quick second. Look at the actual diagram. If you drew your diagram kind of to scale, which I kind of did, I think. I feel like that's reasonable, right? My 10 is bigger than the 6. My 6 is about twice as big as 3. What's the only thing that's not really drawn to scale well here?
The green.
The degree, yeah. This should have probably been like 55, not 35, right? I realize that now, because this angle looks like it's above 45. So that was probably a bad number to use. I should probably use 55. But again, the idea I want you to see is that this person moved up and to the right, then a lot to the right, and then back down. So this person moved a lot to the right. These are both positives. A lot to the right. Then the person moved up, but then came back down. So these kind of balance each other a little bit, yielding a very small solution. What are these numbers actually? What are these numbers actually?
The sides of the resultant.
Yeah, the yellow triangle that we haven't drawn yet. So if I draw in this yellow triangle now, I use a dashed black line on the bottom, and I draw the actual dashed vertical line here. These are the legs. This is 2.75. This is 14.19. Those are the lengths of this right triangle that we've now drawn in that didn't exist before. So our goal was to find the length of the yellow line, and I can do that by finding the two resultants and labeling them as the sides of the triangle that make the yellow line the hypotenuse. How do I find the hypotenuse? If I know the sides, Pythagorean theorem. 14.19 squared plus 2.75 squared, enter, square root of the second answer, you get the hypotenuse length. It's going to be more than 14.19, probably not much more. 14 squared is 196, 2.75 squared is like 8. So it's going to be like the square root of 204. It'll be just a little bit above 14.19. Okay, it's not going to be much more. So let's jot that down so we know what we're doing. What does R end up being there? Do we have a number for it? It's going to be something close, I know that. So up here in the top right is where we're doing our final calculations, right? That's where the stuff actually matters in the end, because we need the overall length of the yellow line and we need the angle. So we're first finding the length. What do we got? 14.19 squared plus 2.75 squared. Yeah.
Around 14.75
Okay? That sounds good. It's a little bit more than what we thought. Good. 14.19. It's got to be more than that. Sounds right. Now, how do I find the angle? The angle of this resultant yellow vector. How do I find the angle? Chris?
That's really the tangent inverse of 14.45.
Close. You're close, Chris. It is tangent inverse. Before we can get to inverse, though, let's just write the trig ratio to help us. It might help, Chris, right? Because tangent and cosine and sine are all ratios. So let's call the angle theta that we're looking for. Here's theta right here. That's the angle theta that we're trying to determine. And if you don't know what we're referring to right now, I'm saying that angle, the angle between the resultant and the eastward direction. I know it's going to be north of east, the answer. So I know my angle is going to be northeast because of the way it's set up. But my question is, what is this angle? And Chris was on the right track. He said you should probably use someone with tangent. Someone with tangent. Does anybody help him out?
Would it be because tangent is opposite of the adjacent?
Good. So tangent theta, go ahead, equals.
Be 2.75 over 14.19.
Well done. And then take the tangent inverse. So it helps to write the trig ratio first so you don't have to memorize it. Some of you have memorized it. And I noticed on your test you wrote that theta is the tangent inverse of y over x. And that's right. Isn't this y? 2.75 is the y. And x is 14.19. So some of you have picked up on that by now, that the tangent inverse of y over x will always give you the angle. And that is true. You can use that. But when in doubt, just draw out that triangle like we did there. We drew in the triangle of 14.19 and 2.75. We drew those in there from these numbers. Then we used opposite over adjacent to write the tangent ratio. And then theta becomes the inverse of that. What does that become for theta? If I do the tangent inverse of that fraction. Tangent inverse of that fraction. What do you got, Aiden? I see you calculating. Give me something. Got it? It's not working? What are you getting, Will?
10.97.
Katie? Yeah? So, Aiden, what are you typing in? Is it giving you an error or something? What are you getting as an answer?
I think I'm not actually degree mode.
In mode. Take a look. Is radian highlighted or degree?
It was reading.
Yeah, there you go. So try it again. Just press second enter. You can just have the calculator redo the same command. And it'll do it in degree mode. It should be 10.97. So how do I give a verbal or final answer for this? I want to write what I have as a solution, but I want to write it in the correct form. So here's how I would write my answer. The overall resultant is 14.45 miles at 10.97 degrees northeast. Okay, that's my overall answer at the bottom. I found the length of the resultant and the angle at which it's aimed, and then I recognize that it's above northeast, it's above east. How do I know it's northeast, by the way? These are both positive right here. A positive x means go this way. A positive y means go up a little bit, and that's what we did with the triangle. Went this way and went up, that's northeast. So I knew to tack on northeast at the end. This is a great sample problem for that. The whole process we just went through is very useful. So if you're even a little bit confused still, I would really recommend use this as a template. You can obviously go back to the lesson on this and listen to that video again, but I recorded this so you can maybe look at this again. But practice the problem after the review document that has an exact setup. Like, I think the person makes like 6 different movements, or 4 different, or 5 different movements. I don't know what it is. Okay, but do the exact same thing with the table method setup. Okay, with the table method setup. Okay. Next one. Other topics, other ideas? Yeah, Rick, go ahead.
I just have a question
Yeah.
on this. So you just add across, you don't multiply.
Correct, because what are we doing, Rick? Ready? We're visualizing that this person in the x direction has walked, ready? This far, plus this far. Isn't that how far they've walked? And 10 cos 35 is right there. And then 6 miles is right there. So if I want to find the overall distance walked, which is this leg right here, it's this plus this. It's segment addition postulate from geometry. You're taking two segments and adding them up to say that they equal the overall segment. And it's the same thing next, Rick. You go up with a positive displacement and then come back down. That's the negative displacement. So whatever this is, plus this negative number, so this plus this number, which is negative, so it's really subtraction, gives you 2.75, which is what's left over right here. Okay? Always adding across. That's the reason back there. So I want you to see that you're adding segments together. You don't just multiply. This is multiplication always. Okay? Whenever you find the vector components, always multiply. Okay? Back until people are ready. So it's a good example of vectors. So we've looked at an example of conservation of energy with the slide. We've looked at a little bit with forces and free body diagrams with the wishing well. And now a little bit with vectors. What else do you want to look at? Yeah.
Like ranking projectiles in order of increasing horizontal components. Yeah.
Okay.
There was a problem that had like 3 vectors.
Yes, gotcha.
3 projectiles.
So as an object, let's say it's here on ground level. One is launched like this, one is launched like this, and one is launched like this, let's say, okay? And let's say here's the ground. And the problem says they're all launched with the exact same velocity. So let's pick a number. Okay? And the question says the following. Which of the 3 launches has the highest initial horizontal velocity? Or it could be the highest initial vertical velocity. It doesn't matter which one. So for all of these problems, what we have to do is we have to consider the fact that we have to multiply by what? What trig ratio for the x? For the x, what trig ratio did we use last time? Cosine. But the problem is we don't have angles, right? And the problem wasn't given with angles on purpose. It was not given with angles. But use common sense and logic here, not math actually. So if we had the numbers, we could do it. Or you could make numbers up. Make this angle 20. Make that 50 and make that 90, obviously. So you can pick numbers, 20, 50, 90. But also consider, we did this in class, when you launch straight up, does it go anywhere this way? It comes right back down, right? When you launch horizontally, it only goes this way. When you launch at an angle, it does both. What did we say? As the angle goes up, what happens? Or as the angle gets lower, what happens? We talked about this in class. 45 was that special angle we talked about also. James, give us a little overall statement.
The higher and lower it goes, the shorter distance it will travel compared to 45. The higher you go, there's more time to take. The lower it takes less time. So it has less. If it's lower, it has less time to travel further.
So it does this if it's low, this if it's higher, and then it goes straight up and down if it does that. Okay. What about the velocity components, though? Tell me.
So in the one that goes straight up, it has the highest y.
It's all Vy on that one. Good.
And then in the lowest one, it's all Vx.
Well, if it were horizontal, yes. This one would be all Vx.
More Vx.
Good. This would be more Vx than Vy, and this would be more.
Assuming that's 45.
Yeah, let's put 45 right here. Let's put a marker. Good point. Okay. So we have 4 cases. If it's fired horizontally, which we've talked about several times now, if it's fired horizontally, all the velocity is in the x. So 10 meters per second would be Vx. If it's fired vertically, it's all Vy. That would be 10 meters per second would be Vy. But anything below 45 is more in the x. So Vx would be more than Vy. Anything above 45, Vy would be more than Vx. So in this problem of a ranking problem, right? Ranking, the most, this would have the most velocity in the horizontal, the next most, and the last most, or the least, I guess you would say in that case. But for the vertical components, most vertical, less, none. Okay? So as you increase, more vertical component velocity. As you decrease the angle, more horizontal. Take like a 2-minute break. Get some water, at least stretch your legs, guys. We have a second period. Test number 6.
Yeah, the most recent one.
Okay. Yep. Did any of you guys test 6 yet, actually? Did I give you test 6 back? I don't think I ever did.
No, you just
No,
showed
right? I didn't give you. Remember I showed you grades yesterday? Was the only grades I showed you?
Yeah, you only showed the grade.
Did I give you a grade, Chris?
No.
Let me bring a grade in then in case you want. But I can't give the test back yet. That's the only reason. But I will put the math solutions to it up today as soon as she's done taking it. So you can look at the math problems, and if you want to come in tomorrow morning or tomorrow from school to see the test, you can do that for sure. Because I don't see you guys tomorrow in class. Yeah, you never got it back, so I only gave grades back. I'll bring the grades in and I'll show you all the grades.
Are you able to update the
Possibly. I was trying to finish your labs, and I have like 6 or 7 left to do still. So it really depends on when, because I want to grade your project reports today. Whatever the project you wrote the report up, and then last. Those are the only things I've left. Problem sets are done, all that stuff is done. But I don't want to give you the grade back or give you an updated grade because the project is a half test, so it really affects your grade. So until I actually incorporate that, I don't want to give you guys that updated numbers yet. But as soon as I'm done with the second quarter grades, I will definitely let you guys know. Whether it be email or something like that, so this week or next week when I combine to see an update, you can do that. But obviously don't base your exam performance on your grade, so I'm not gonna, it shouldn't affect you now.
So
You have it, yes, I agree. Yeah, I remember you emailed it that day.
Yeah, then we get up.
Are you serious, Mike?
Was it bad?
Are they Saturday or Sunday?
Was it? Oh, it's crazy. One of those like fast.
And this was on time. You emailed it to me the day that it was due this route. Yeah, I remember that. That's right.
Tomorrow.
No, it's today. It's fucking today. You don't know yours, but
Will, he's saying there were oral labs. There are oral labs.
Oh, yeah, after school.
That's what I was saying.
I thought you meant like the beginning of the
Oh, no. So we have to take oral labs. That's why I have to do both.
it's a B-day.
Wait,
I'm not allowed to
Dude, are we even able to study for the oral?
What?
Dude, how are we supposed to do only oral? We don't even know if we're gonna
I didn't know there today.
Give us the question.
I'm gonna go to 0. What the hell?
Yeah, she didn't get this name.
Ricky.
Alright, so I've got all 5 tests here, so you kind of have to just tell me what you want to see and what you want to work on individually.